Everyone. Welcome to lecture 9. We will conclude our discussion on calculus of subgradients and building on the homework discussion, go on to local and global minimum. Actually, the optimization problem, look at sufficient condition for global minimum, connection with subgradients, then oh, move on to convexity and global minimum and so on. Something's wrong here. Okay. Um, Then we move on to algorithms for optimization, first order and thereafter. Okay, so did anyone attempt this homework problem?
Yes,
Yes.
at
Yes.
least
So
for the first year.
yeah, the first one. So what is the idea? How did you try attempting it?
Uh, so Q of x is a vector Q1 to Qk of
Mhm.
x bars. So we can let's say each of these Qi have a subgradient Gi belonging to its subdifferential, and then we can use the basic definition that Fy is greater than equal to Fx plus H transpose y minus x, and follow up with that. It's basically
Okay,
I got a like a kind of a dot product between the how do I say the subdifferential of P and each subdifferential of Q.
that's how you'll get the subgraded sub differential of f, right?
Yes.
Okay, so let's do that. Right, so these are parallels. One based on the P being convex and non-decreasing while Qi is convex, and other is Qi is concave, P is convex and non-increasing. I'll present the results, but exactly the spirit of what was explained just now. You'll have the result for the second case as well. And yeah, we had listed some examples of this property, but now we are interested in deriving the subgradient. So let's look at this. So second one is homework in the sense that I'll give you the solution. You can try and understand it as homework. Okay, so exactly as was told, suggested by one few. Um, the first case. So the goal here is I want to find the HF. So f is a function called proposition function such that P of Q of x, which is fx, um, plus HF transpose, which is what we want to find out. Um, x at x into y minus x is a lower bound for fy. Okay, so just remember that this expression is nothing but P of Q of y1, um, 1 of y, qk of y. With that understanding, how do you get your HF? So the first thing to realize is that each qi plus qix, right, plus hqi transpose y minus x is also scalar. So we can go through that intermediate step. So the first step we will do is identify that okay, we would know expect each of these QIs to be also convex. QI y, which is greater than equal to yx plus, I know that QI is convex in the first case, so HQI transpose y minus x, that subgradient will exist. So since each QI is convex, okay. So we just expanded this one of them, or one of those arbitrarily. And then what we'll do is look at the fact that P is non-decreasing in each argument. Okay. So this is step number 1. Step number 2 is rather P, not each. There's only one P. P is non-decreasing in each argument. So what will this imply? And the fact that P is also convex. That's a third point we'll make use of.
So this would imply that gradient of P with respect to Qx is positive.
Right. Gradient of P with respect to
Qx.
yeah. So P is convex and it also has its subgradients. So based on this, let me write down the expression. So you'll expect that P of R plus W is greater than or equal to P of R plus HP at that point transpose at R. The whole is a function of W. Hope this is clear, right? So what we are doing here basically now is writing. So I'm going to expand this. So what we have basically is P applied to this vector Q1 X QK X. Okay, and this is basically my R. When I talk of an R, this is my R. And then plus this I'll add this HP transpose R Q, right? So that basically that's the W part basically. So that will be H Q1 transpose Y minus X HQK transpose I minus X, and this is my W. So just use shading here. So this part is the R we are talking about here. Okay, the R here, and the W part is this entire component here. Okay, the rest is straightforward. We applied this. Basically, you need to compose this each, considering that each Qi plus HQi transpose Y minus X is a scalar. This entire expression is a scalar. Okay, so basically applying both of these together, you're done. So this what you get here, Fy f at y is greater than or equal to p of all this. So now they have this argument sitting inside, and then when you basically expand that by monotonicity, that is because p is non-decreasing in each argument, the inequality will continue, and now you'll have this new composition as a subgradient. This is going to give you the composition subgradient. Hope this is clear. Okay, so the subgradient is basically this HPI. If you take the ith component here, ith component from here, multiply that by the ith component HQI. This is a subgradient of the composite function at x. Of course, now you have to sum over all the indices. Okay, remember that HQIX itself is a vector. So we are summing multiple vectors scaled by the weights HPI. Any questions? So we can be rest assured that this is in Rn, the original space in which X was lying.
Sir, if P or any of the Q's are not differentiable, do we also need to like take the convex hull of this set, because this would be a set in that case, right? Each possible subgradient of
Good
each of
point.
the functions.
So first note that this is just a subgradient. Okay, it's not so for every possible HQI HP, right? You will basically have to consider this sum. That will basically give you a convex hull. So this is going to be a closed convex set. Okay, this is only a subgradient. Let me complete that story. It's a good point you made. Over all such HPs, right, and HQs, basically when we enumerate, right, let me say enumerating all such HPs and HQs, because they themselves may be multiple. There's a subdifferential for a P, there's a subdifferential for Q, gives us the closed convex subdifferential for F. Does that help?
Yeah, like this would prove that this closed convex set is a subset of the set of all possible subgradients. But how can we prove that every subgradient is expressible in this format? We haven't proved it the other way around, right?
Yes, good point. Good point. So this is just giving you one way of deriving the subgradient. You're very right. There could be multiple other subgradients. Yeah, right. That was your point.
Yeah, like this set need not be the complete set of uh, subgradients. At least we
Yes.
haven't proved that yet.
Yes. Yes. That's a good point. But nevertheless, this gives us a closed convex subdifferential. That I mean, it or subset of the subdifferential. Maybe to be more precise, right?
Yeah.
Closed convex. Let me be even more precise. Gives us the subset. Gives us a subset. Very good observations. Yeah. Because this is just one way of deriving a subgradient. In fact, a lot of subgradient descent algorithms just hinge on deriving one subgradient. There could be multiple. Thanks. Any other points? Okay.
So essentially, this is not the complete set of subgradients, or can we prove otherwise that this is the?
So this is effectively all the subgradients. Yeah. So to prove the tightness, we can show that there are no other subgradients. I mean, I don't recall off the top of my mind how you prove that. But from what I remember, this is the exhaustive set of subgradients. But the proof we have is only for existence, not enumeration. Is that okay? Oh. Okay. Um, we'll proceed. Okay, so you can do the other way as well. As homework, I want you to understand the other part. This is a little trickier. It's just because now we are dealing with concave QIs rather than convex, right? So you'll have to use the reverse inequality. So you have to use this. Qi y is less than equal to Qi x plus HQi transpose y minus x because Qi is concave. The rest remains the same. And I mean, you still find the same. It just boils down to the same expression. So only thing is HQi is not called a subgradient, it's called a supergradient. Okay, it's giving you an upper bound. This is a supergradient, a concave function. Gives a upper bound. Okay, any other question on this? Otherwise, I'll proceed. Okay, so let's move on to the next, which is proximal operators. These are again very interesting, very useful when it comes to analysis of constraint optimization. So if Cxy is convex in X, Y, and C's convex set, then the distance of a point X from the set C, right? I can show it. Let me illustrate it. This distance. So this is a convex set. This D here is this distance. So let me draw that D. Is a convex set. Sorry, convex function. So now for this, how do you compute the subdifferential or subgradient? Any thoughts?
Sir, is this distance like minimum distance?
This is the minimum distance, infimum. So it's possible that this set C is not closed. It may be an open convex set. Okay, so then therefore we look at infimum. So let me show an example. A good question. Why infimum, right? So let's say this my set C was like this. This is my set C, and my point X is in the same plane. Okay, this is an open circle, convex set, open convex set. So this X, the distance of X from the C. I mean, unless you do infimum, there's no minimum. Minimum is not defined. So infimum makes sense. Is that okay?
Yes, sir.
So this is minimum is not defined. Especially when the point X is in the same plane as C. Hyperplane as C. Okay, very good point here. So this justifies the use of infimum. So this D is a convex function, and now what do you do with the sub differential or subgradient? Okay, so this you can write it differently. Minimum over a of this function x in c can be written in terms of an indicator function. Okay, you can write this as minimum of some function. Say here you see this function prox ax such that x in c is convex set. Okay, this can be written as the same as saying min over x of ax plus an indicator function over c of x, where this ICX is 0 if x is in that set C, and let's say is infinity otherwise. I mean, you'll really not pick such a point, right? Because if IC is going to infinity, you are violating the constraint and you'd rather not go to such a point. So this is how we kind of totally deter violation of the constraint. This is how it's translated x in C, so that is a convex set. The special case is when, for example, if this is a prox function. A special case is when you basically take the indicator function. So this prox can be thought of as a surrogate or approximation to the indicator function. This prox. So instead of saying indicator, I'm saying okay, fy plus 1/2 x minus y. Approximation the indicator. Okay. So this is a special case. Special case is when we have fy is the indicator function. Right, so you want to eliminate constraints of an optimization problem. So in such a case, again, so in such a case, we resort to this normal cone. So there's something called a normal cone which gives you the set of subgradients. H transpose y says that, sorry, H such that H transpose y is greater than equal to H transpose Z for all Z and C. This is a normal cone. This is a normal cone. Okay, so I mean we'll use invoke something like this when we talk about the proximal gradient descent algorithm, but we'll bring it up later on. But this is also part of subgradient calculus. Again, I'm going to leave some of this as advanced and optional, like perspective functions. So I mean the sky is the limit when we talk about calculus of subgradients. But let's say I have this perspective function which is dealing with when I, let's say I have some text like this. Good morning is written here, and I'm seeing it from the side. Okay. Now when I see it from the side, obviously all the good morning pixels are basically collapsed into one. That's a perspective transformation. An example of perspective transformation. This perspective transformation turns out to be this function that does this transformation is an example of a perspective function, which is a convex function. How does it look like? Perspective of function f is this function g. Now what g has done is it's added one more coordinate to which to project. Now I have shown a side view. You could have taken maybe a top view or a slant view, right? So this t is giving you the kind of view based on which you are uh, ingesting the text. So the t is like the view, the extra dimension here. And what it's doing is it's just pre-multiplying by t and dividing the argument by t. So this is that perspective transformation. Now example is if you have fx as x transpose x, its perspective is x transpose x by t and it's convex. Okay, so likewise the perspective of negative logarithm is called the relative entropy function, and t log t minus t log x is also convex. No, it's related to what we also know as cross entropy. You can view cross entropy as a perspective transformation. Okay, so what about the subdifferentials here? Right, so think about this. I mean, again, it's going to be optional. I will not insist on this. But let's move to the next topic, unless there are questions here. So this is giving you some glimpses into subgradient calculus. But there's another interesting aspect about subgradient kind of functions. Talk of a notion of monotone vectors, a monotone function, which are vector functions. Let's draw an analogy. So if talk of convexity, one way of understanding convexity is that f dash x must be increasing, strictly increasing. So slope keeps on increasing. That's convexity. Right? That's a slope. Now, is there an analog for f going from Rn to R? Anyone? Any thoughts? So is there an analog? So can we talk of strictly increasing subgradient as a straw man, right? It's a vector. Can you talk of that? Every component of the function should keep increasing. Anyone? That will be a bit limiting, right? It's like saying, okay, I have f dash x minus f dash y, whole thing to y, sorry, x minus y. Right? This should be greater than, strictly greater than 0 or greater than equal to 0. But this, I mean, you can say for all x which are, oh yeah, this basically means that this basically saying that f dash x is greater than f dash y for every component when every component of x is greater than every component of y. It's a bit limiting and doesn't make sense. Okay, what could you do as an alternative? So I'm going to strike this off. This doesn't make sense. What could you do as an alternative? Can we talk of something else? Then we talk of monotone vectors. And it turns out we can. Okay, so you can view a subgradient as an instance of a general function h going from D to Rn. There is a subset of Rn. I right, and then we can talk of monotonicity of h as follows. So instead of saying okay, the product right for is greater than or equal to 0, which doesn't make sense for every component, right? I mean this was a component wise inequality. So what we had written with component wise product and inequality limiting. But what we are doing instead now is saying okay, instead of component wise product and inequality, how about I taking a dot product of the subgradient of f at x, the subgradient of f at y, and x minus y. That's exactly what we're doing here. So you're saying the dot product. Okay, so instead of component wise, we have dot product, and looking at the subgradients here instead of f dash, right? Instead of saying f dash for every component, I'll say okay, the entire vector itself. This is called a monotone. I mean, you can have a strictly monotone variant. So what you do in strictly monotone is you change this to greater than, and you get strict monotone. Okay, so with this, you can also define a notion of uniformly or strongly monotone. Like we did before, we had a strong convexity. Now we can talk of strong monotonicity. Basically, you're saying that this vector will always make a acute angle, not an obtuse angle. Okay, so let's the thing in terms of angles. This is like saying the angle is always acute. In fact, it will never be zero. No, never be 90 degrees. The angle is always acute, whereas here we are saying that the angle will be lower bounded by a quadratic function. I mean, it's not really angle but dot product, right? Angle will be lower bounded by some quadratic function in the numerator. Denominator again, you'll have to have the norms, etc. Spirit in simple plain English. Based on this, now you can come up with subgradient notion of convexity in terms of monotonicity. F is convex if and only if gradient is monotone. You can talk of subgradients also. Yeah, but strict monotonicity becomes a tricky thing. Subgradients. So they also hold in general for subgradients as I've more. We'll quickly show them only for gradients. I mean, we can do it for subgradients, but as I said, tricky. HP is called a proximal gradient of f if and only if for all y in domain of f, fi is greater than or equal to fx plus this dot product hp y minus x plus minus lambda by 2 norm of y minus x square. So there's a notion of proximal gradient as well. Let's not get into that. So all that I marked in red is advanced, but the part in blue is fairly intuitive. I mean, as I said, the intuition is from one dimension of a strictly increasing gradient or derivative. It doesn't make sense to talk of every component, so we are talking in terms of dot product, which is the same. You can show that a special case is in one dimension. In one dimensions is easy to see. Basically, amounts to increasing or I mean strictly could be in bracket, right? strictly increasing derivative. Okay, yeah, that's what I've tried to show on the right hand side here. Okay, so I mean I'm not going to go over all of these proofs, but as a homework, you can look at these. I've also provided them in the Moodle notes. So for necessity, I'm going to run through it very quickly. Right, so necessity, what you do is just write down. Okay, if it's strongly convex, we start with the strongly convex case, write down, and I just add these inequalities. So what would happen when you add these inequalities? Yes, some things will get cancelled out. These parts will get cancelled out. Fi, fx. So it's very simple, right? And you'll have this difference of the two gradients. If you add them, you get the difference of the two gradients because of the flip in the sign. Here it will be minus y plus x. Okay, so then you'll get you'll basically get c by 2. Yeah, sorry. C and half c will become just c. Okay, so this is very simple. So basically the fact that dot product is lower bounded by some angle in the numerator. Sorry, is lower bounded by some quadratic function for the angle in the numerator. So to prove sufficiency, little bit harder work has to be done, but we can apply the mean value theorem. And very interesting part here, I think I want to just highlight the interesting learning here, which is that you can project everything to one dimension. That's interesting. So you deal not with f, but you're dealing with this function phi, okay, which is operating in one dimension. It was basically showing my mean value theorem that f phi 0 is fx, phi 1 is fy, right? This phi 0 is fx. Phi 1 is fy, and phi 1 minus phi 0 is just phi dash t, right? By mean value theorem, there will exist such a phi dash t, okay, which will just turn out to be the dot product. Okay, the dot product basically. Okay, that's why this result itself was there, because this dot product what was corresponding to uh, the phi t in the mean value theorem. Okay, so rest is all here. I'll not spend more time. Okay, so you can basically use this result to show that f is convex. And sufficiency is basically we use monotonicity of gradient. Okay, in addition to the mean value theorem, we basically made use of the fact that there is monotonicity of phi of f. Sorry, f of gradient of f. For the case of strong convexity, there's a little bit more work you have to do. So not only you're looking at the mean value theorem, but you'll have to also now look at some quadratic expansion and then do some integration. Okay, so across all values of t, so that you get this quadratic lower bound which is independent of t. So what we have done is to move from Ct y minus x norm square. You've basically integrated from 0 to 1 of Ct. Right, so now this is in terms of t, y and x are fixed. This is expression 1/2 c y norm of y minus x square. So that's the only additional kind of work we need to do. So any questions? So this kind of brings us to some more analysis of gradients, subgradients, monotonicity, their relationship in a definition of monotonicity, sorry, convexity in terms of monotonicity of gradients or subgradients and so on. I think we'll now move on to optimization. So any questions? Okay. Okay, so now let's look at optimization a little carefully. Now this is a plot of a function 3x1 minus x1 square minus x1 cube minus 2x2 square plus x2 raised to 4. And you can see this function has several local minima and maxima, right? So let's try and plot those maxima here. So you can find one maximum here. Okay. I mean, some of them are hidden here, you can't see, but there could be more as the function grows further. But it also has lots of minima. More of the minimas are seen here. There's one, then there's one here. Local maxima and minima. So we all know from our basic calculus notion of absolute maximum and minimum, but now you can talk about function of multiple variables and extend the same definition. So you have a notion of absolute maximum with respect to a set D, right? So domain has to be very clearly defined. You can also have an absolute minimum at C if fx greater than or equal to f of c for all x and d. Right? C is called the point of absolute minimum. You can also have local maximum, but that requires you to have a ball, and not just a ball, an open ball. It contains a C. Okay. So let's say I have this function, and let's look at the maximum case first. So this is the FC, right? Maximum value it has. Now you need an open ball B, for example, in this case. In the one-dimensional case, you can easily understand this as all x says that norm of x minus c, but you're not looking at less than equal to, just strictly less than epsilon. Okay, a small ball around it. And what would that amount to here? It will basically mean a small region around this. A non-trivial region. It cannot be zero. Non-trivial region. So now why are we talking about open ball? Well, it's local. It's possible that as you, as you move further away, you either violate a constraint or you move outside the domain. Okay. A local maximum is in terms of again an open ball, but the inequality is flipped. You can dip down somewhere else, but this is my FC, local minimum. You could also have an extreme value, which is either a local maximum or local minimum. Now, what is the relation of subgradients and global and local minima? So we'll quickly look at subgradient based sufficient condition. We are not looking at gradients alone. We are looking at subgradient, the larger class. So we are kind of generalizing. We are starting with the most general statement. For convex functions specifically, we have that at a point of local minimum is also a point of global minimum. For a strictly convex function, there is also a unique point of global minimum. Okay. Let's understand this a little bit carefully. Okay, so going back to our old figure, right? We find that the function has many possible linear tangents that may form a lower bound. So that's how we define the subgradient, the linear tangent lower bound. So question is, what is its connection, right? It's a minimum of the function or minima of the function. I mean, the relation is a little obvious in this inequality. I'd like you to suggest. This is could be open for discussion. Yeah. Yes. Anyone? This is very simple. You should get it.
Like if the set of subgradients has the horizontal subgradient as well, then it is a point of minima.
Right. If there exists a horizontal. Now, when you say horizontal, it is in this function view, right?
Yeah, like as in the graph right now, so parallel to the x-axis.
Horizontal lower bound parallel the input space. All right. At the point of uh, minimum. Then you're saying x must be a point of local or global.
Should be local, because like, unless we are assured the function is convex, we can't.
Okay, but just make a note that we are talking about for all y. Fi is greater than or equal to fx plus h transpose y minus x for
Okay.
all y. Okay, so if you want, put a x subscript here. Okay, this is at x. So do you want to revise? Is it local or global?
Yeah, global.
Okay, so some points are important. Moment we have, we'll show this more formally, but moment we have a for all, we can take a little bit more liberty. Okay, and then what this basically is saying is that there is a horizontal lower bound. Horizontal lower bound basically is saying that there's no rate of change, right? Like saying no changes to the function value on small movements around x. What would that amount to again? I mean, just equivalent ways of saying thing. Right? Can I say that this would amount to a zero subgradient? Or when I say subgradient vector, which is zero, the zero vector. I'm kind of also alluding to the discussion below. Right? This horizontal lower bound parallel to the input space, right? This is in the function space. So note that this is all in the function space. Okay. So let's actually show this formally. Okay. So if for a convex function f, the moment you say convex function, it has a subgradient. Okay. So moment I say convex, I take the liberty of writing down my subgradient based inequality. and I'll say for all y in the domain of f, it should happen that f of y is greater than or equal to f of x plus hx transpose y minus x. So now if x there exists, okay, now there's a formal statement I'm making. There exists 0, which is an element of the subdifferential of f at x, right? That is hx equals 0 is a valid subgradient. Then what can I say? F of y, again I'll be very conscious, I'll just copy this whole thing. Everything is the same except that f of y is greater than or equal to f of x for all y in the domain of f. This is the key. So then that basically is now showing that x is a local minimum. Okay, so it's just saying the same thing here again. If fx star is min of fx, then right, if 0 belongs to a subdifferential of f x star, then fx star must be the min of fx. That h is 0 being a subgradient for all y, right? Exactly what we wrote in the previous slide would mean that f of y is greater than or equal to f of x star plus 0 transpose y minus x star, which is f of x star. F of x star must be a point of, x star must be a point of minimum. Okay, that's exactly what we wrote. So we have a special case of this, which we all are aware about. The case of differentiable f, in which case a subdifferential is exactly 1 point or 1 vector gradient of f at x. So if the gradient exists, if the function is differentiable, then you just set it to 0, you'll get 1 point x. In fact, you could get multiple points even as solution to this. Question is there a necessary condition for a differentiable function having a local or global minimum at x? Right, this is a sufficient condition. So let's just let me just change this color to, all this is basically a sufficient condition. This is only a sufficient condition, not necessary. Okay, but what if I wanted a necessary condition? So a little later we'll talk about, we'll deal with it. We'll need some more equipment. So let's start with sufficient condition, which itself is a good thing for us. And now we'll apply it. Okay, let's apply it to lasso again. Okay. And we will in fact very soon get an algorithm. So there's a lasso problem, which is again I've simplified ax to just x. Okay, the same old problem which we simplified problem in the last class. And we had written down the subgradients of fx. H is x minus y plus lambda s, where si is a sign of xi if xi is not equal to 0 and si is between -1 and 1. Exactly the same convex hull, right? This is basically a convex hull for subdifferential. Okay, so this so far so good. Now I would really like you to work on this. I mean, please, all of you, if you have notebooks, write this down. This will be very helpful. I'd like to draw your attention to some component, some parts of this here. Okay, so this, you might recall that this lambda x1 is what gave you this lambda s. So keep that in mind. And this, what we are going to do is look at this expression, look at cases. Okay, we have different cases corresponding to xi not equal to 0 and xi equal to 0. And we are going to basically now make use of what we have derived with the previous slide, which is a sufficient condition. So this is based on, when I say solution to this problem, it's basically based on the sufficient condition of the previous slide. But we want to apply it and get hold of a kind of solution. What exactly is happening? Okay. So let's write down. I'm going to highlight this as case 1. Case 1 is si sin xi. Okay, so let's call this case 1. This entire expression. Okay, and we'll likewise write down something for case 2. So what is the expression for case 1? Yes, I like participation at this point. So I want to basically set this entire thing to 0, right? How do I set it to 0? Based on these cases. Now xi, now we are talking about xi star, a point of solution, right? So which satisfies a sufficient condition. What would you expect in that at such a point? So this is case 2. Okay, anyone? So let's write down like what happens if hi is 0. What happens if hi is 1? Yep, I mean, or non-zero, right? What I meant is non-zero. So if, but let's start with hi is 0. That should give us pretty much everything we need. If hi is 0, and then now look at the cases. If xi is not equal to 0, that itself can have two cases. Okay, I'm going to now expand on this a bit more. Okay, so let me use the pink color itself. So I'll have two cases within case 1. If hi is equal to 0, and let's say xi is greater than 0. You can help me if hi is equal to 0 and xi is less than 0. So you can feel free to create more cases. Okay, so can we come up with some cases for each of these? Yes. I need your help to complete this. So can I say that hi, if it's equal to 0 and xi is greater than 0, which means that si must be plus 1, right? The si as per the case 1 is sine of xi, which must be plus 1. So this is the same as saying what? Hi which is xi minus yi. So I'm talking about the ith index, okay? Xi minus yi plus lambda si. Here, lambda si is going to be just lambda. Okay, so this implies that the first case, which is equal to 0, is xi minus yi plus lambda, which is equal to 0. This is if and only if, okay, it's bidirectional, if and only if. Now we are trying to come up with a solution. If and only if xi equals yi minus lambda. Again, so I'm putting the now the onus earlier was hi equal to 0 and xi equal to 0, xi greater than 0. I'll now put the onus on yi, right? So xi equals yi minus lambda. If it has to be greater than 0, it's like saying that xi equals yi minus lambda and yi greater than lambda. Okay, just note this. Now, how we have gone from, I'm just going to annotate this. Okay, so just note this here. We had xi greater than 0. Hi equal to 0 got used, so that's consistent everywhere. But here I have flipped. I have gone from xi greater than 0 to yi greater than lambda because that's what we know. So let me just change this to if. This if. That's where we began. Okay, so this should be easy to see. Call it xi star if you want. Xi star is yi star minus or yi minus lambda if yi is greater than lambda. Now I can complete the other part very similarly. So I'll say this has hi equals xi minus yi minus lambda, just because sign is going to be negative if xi is less than 0. Okay, so note this, right? So if this is the same thing, if or else if, and the rest is similar. Okay, so now I'm going to similar in the sense signs will get flipped. So then we'll have xi equals yi plus lambda. The sign associated with lambda has got flipped. Now this has to be less than 0. Okay, if and only if xi is yi plus lambda, if now that if has become yi is less than minus lambda. So this is explaining the case 1. What about the case 2? If xi equal to 0, what happens in case 2? Anyone? It's all case 1. Case 2 is xi equal to 0. Xi equals 0 means si is between -1 and 1, right? Case 2. I want to know what is that x where the solution is. Well, point is not an issue at all. If xi, I mean, you're perfectly fine if x is 0 and h is 0. Case 2 is what? Nothing but hi is 0. You want that's sufficient condition. You stand by it, and xi equals 0. Now, when will this happen, right? So you just need to write this down. So hi. So now, what you write for s here is tricky. So let's just finish that. It's minus y. Okay, minus yi plus lambda si equals 0. I think I've been missing the 0 some places. Equals 0. Let me just shrink this and okay, this was meant to be equal to 0. The previous line as well. Okay, going back here. So this what will this turn out to be? You'll just get hi to be 0. Yes, somebody wants to say something. This is si. Yes, somebody wanted to say something.
No, sir, I was just going to say the next step.
Yeah, please go ahead. Please prompt it.
So we'll get yi is between minus lambda and lambda for case 2.
Right. So this is like saying xi is 0, and this if si is between -1 and +1, and if this sum has to be 0, then it's the same as saying if yi is between minus lambda and plus lambda, and if xi is equal to 0, right? Good. Okay, so now just let me just move these parts together. So this is basically what we want. Let me just move this here. This entire thing on the right hand side is our solution. Yes, I'm just going to box this part and read the solution. We basically are saying the solution based on this subdifferential is that if yi is greater than lambda, xi is yi minus lambda. If yi is less than minus lambda, xi is yi plus lambda. What are these two saying? Well, if yi is too positive, then shrink it. If yi is too negative, then grow it by lambda. But if it's not neither too positive nor too negative, it's between minus lambda and lambda, let xi become 0. That's a sparsity. Okay, so this last statement is giving you sparsity. Sparsity in this in this closed interval. And the cases 1 and 2 are basically saying shrink. Shrink beyond the closed interval. So in plain English, right? Case 1, shrink. I mean positively or negatively, right? Shrink beyond closed interval. So I hope you were able to follow this discussion. A simple application of our all our calculus so far.
So this solution is the motivation for IST algorithm?
Yeah, this is exactly. So there's an iterative soft thresholding, which is for lasso. There's a motivation behind that. Yes. Let me make a note of that here. Anyone else? This is a good point. However, I must tell you that we have not yet evolved an algorithm. This is right. Tulip, I think you made a good observation. This main motivation behind the iterative soft thresholding algorithm. But there's this, we still don't have an algorithm. Actually, write this as an algorithm, we need something called proximal gradient step. Is I would say this plus proximal gradient descent algorithm. Together give you this iterative soft thresholding algorithm for lasso. Okay. You probably come across in your machine learning class. Okay. So this is in this the name iterative soft thresholding is also embedded here. This is called the soft thresholding operator. This whatever we derived on the previous slide, I've now written it in the form of a very specific operator. Okay. So what is it saying? It's just saying that, well, I mean threshold, basically threshold the value of y and then assign it to x. Okay. So now you apply this iteratively in this proximal gradient descent algorithm. Any questions or comments? Any other comments? Okay, so I mean, obviously we want to know if this converges. Why will it converge? I mean, it's just some random, fixed point. Basically, you're trying to get to this fixed point, right? Well, I mean, it's motivated by this fixed point, but there's a principled convergence analysis also. The questions, let me know. Otherwise, we'll move on. Okay. So now what we'll do is look. This is all sufficiency. All we did it was sufficient condition test. But I mean, that's necessary. This is the way to get the answer, right? How do you prove that? So now we'll move on to the next, which is any point of local minimum is also point of global minimum. And for local minimum, our necessary condition is that gradients must vanish. So overall, for convexity, this is also giving you a necessary condition. Necessary condition. In fact, for convex regions. How do you prove that this is okay? So this is for non-convex and convex, both these apply because we are talking about convex regions. Okay, so let's now prove the next statement. This is my pen. So let's say x is a point of local minimum and y is a point of global minimum. And what we want to show is that this point of local minimum solution is actually also point of globally minimum solution. So I will pivot on an image. Let me, yeah, for want of time, basically we'll save some time by using an image I've drawn beforehand. Okay, so this is the image I would like you to bank upon. And how are we going to prove? So the idea behind the proof. So idea behind the proof is that we'll say, well, if your point of global minimum is different from your point of local minimum, you can actually find another point which is a point of global minimum. So you're constructing. What is the idea behind the proof? Construct a point, hypothetical point Z. Okay. You can show it by treat it as a proof by contradiction, but I mean I'm making it simple here, right? So you're constructing a point Z and that this is within the open ball. The open ball that I've seen here. And what we are trying to show is function at the point Z will actually evaluate to be less than that at X. But X is the point where we are a local minimum. Within the ball itself, we have a local minimum, another new local minimum. Why? Because you are claiming there is a Y which is different from X, which is a global minimum. Right. So this is just because I claimed that f of y is less than say f of x. Okay, so this is the idea behind the proof. Okay, so you're saying there's an fi which is less than f of x, y is outside the ball somewhere else, it's not local minimum, fine, but I'm giving you a z which is within the ball, and I'm contradicting your original point that x was a point of local minimum. All of us know that local minimum means there's a ball of radius epsilon around x, right? So this can be treated as a proof by contradiction. So I would like you to help complete this. How would you complete this? I mean, here I'm saying we'll bring convexity. Rest of the proof requires convexity. How do I show this by convexity? Yes.
So, sir, if for z we have some lambda such that z is lambda x plus 1 minus lambda y.
Right. So
Plus
I'm
or
just going.
equal
Right. Go
to
ahead.
lambda fy plus 1 minus lambda fx, and since fy is less or equal to fx, we plug that in and get that fz is less or equal to fx.
Good point. Yes. You could also do this by midpoint convexity. Yeah, I mean the midpoint, etc. But yeah, this basically I just want to find that z which just marginally pulls me inside x, and then use a convexity. Okay, so here's the so I'm just reproducing this same image here so that you can. So yeah, so there's an epsilon ball around x local minimum such that for all z within that ball z minus x which is less than equal to epsilon, f of z must be greater than equal to f of x, right? That was a contradiction. But now I'm now going to construct a particular point z, and what is that point z? A convex combination theta y plus 1 minus theta x. But the key here is this value. This theta is my point in the counter argument. I have a theta which is epsilon divided by 2 y minus norm of y minus x. Okay, and I can show that this theta will get me my z to be within the ball. So since x is a point of local minimum, and since f of y is less than f of x, because we said there was a different point of global minimum, so it must be that norm of y minus x is greater than epsilon. So now if I take theta to be less than half, then I'll find that z minus x norm is equal to exactly equal to epsilon by 2. So I basically found found a point z within the ball. For this choice, I have a point within the ball. And that what is that point? A point found a point which is a convex combination of x and y within the ball. Now the only step remaining is to show that for such a point by convexity of f can we show that f of z is less than f of x. Okay, that's the next step, and it turns out that's very simple. So So I'm just again important to keep this in mind. So since f is a convex function, what can I say? F of z is less than or equal to f of theta. Can't find my pen, where it disappear. Sorry, I'll have to. I just can't find my pen somehow. Misplaced it. So f is a convex function. I know that f of z is less than or equal to theta times f of x, right? Plus 1 minus theta times f of y. But we also know that f of y is less than f of x. Okay, so let's just continue this. So I'm just going to give you the context again here. So f of x z is less than or equal to theta times f of x plus 1 minus theta times f of y. F of y is also less than f of x. Now the rest is simple. What would you do? Just apply the two together, right? Combining the two. F of y is less than f of x. Just substitute it here. You'll basically get f of z is less than f of x. That's it. Substitute or less than, right? Because less than, strict less than is because of this being less than. Okay, that's it. The two equations imply that f of z is less than f of x. So then how is x a point of local minimum which is different from a point of global minimum? It's not possible. So that's what we have written here. F cannot have a point of local minimum which does not coincide with the point y of global minimum. This is a key. Any questions? Okay. Now let's apply this. We are pretty much ready. Before we apply, we are going to just look at one special case, which is strict convexity. Now, if a function is strictly convex, then it looks like the point of global minimum is unique. You cannot have multiple points of global minimum. Okay. And in fact, you cannot have multiple points of local minima. I mean, either by going by the same count. So what would you prove next? What's your next step going to be? The point x plus y by 2. Right now, this is a point I'm going to show that if the 2 points of global minimum, I actually end up getting a third point, which is at which the function will evaluate to a smaller value than the previous two value. Right. The logic is we have constructed. We show that by strict convexity that we have constructed a new point which is x plus y by 2, which has function value lower than the previous T2 claimed points of global minimum. So we're not talking about local minimum anymore. Now this is a contradiction. So you should be able to show this very easily. This is by strict convexity. F of x plus y by 2 by midpoint convexity. It's exactly the point of midpoint convexity or midpoint strict convexity. Okay, so now that we have set up the context, I mean, do global minima always exist, right? Well, it's not even necessary if f is bounded from below. E raised to x is a classic case. Now e raised to x, the function of course tends to infinity on the right, but as x goes to infinity, it's actually tending to. Okay, sorry, I don't do it using my mouse, but it's going to be like this. It's not even bounded. It's bounded from below, but it doesn't achieve that lower bound. So when is that global minimum achieved? if f is a convex function and there's a non-empty and bounded sublevel set, that f has a global minimum. Okay, so we're going to discuss a little bit more on this in the next class. But what I'm going to leave you as homework is to show that if f is convex and differentiable, then the gradient is a gives you a point of the gradient vanishing at a point means that's a point of global minimum. Okay. So you can use the first order property of convexity to see this. And thereafter we'll now move on to characterizing optimization problems, constraint optimization problems, and more generally convex optimization problems. Okay, I'm going to stop here. Any questions or comments before we conclude? We have 1 minute left. So my homework problem for you is delve a little bit more. You don't have to try and prove. So homework, think of no or enumerate. Think of / enumerate. I know lots of convex functions lots of functions, convex and non-convex, and deliberate on when you can realize a global minimum. And then also try and realize the Weierstrass theorem, right? What does it mean to have for a convex function there? What does it mean to have a non-empty bounded sublevel set? Okay. If there are no more questions, I'll leave it at this point. Thanks, everyone.